a learning experience for all of us. Okay, let me see from current slide. Okay, so I think we're on the way now. So let's address that. I did record the class that we had on Tuesday, and it only went for the 2.5 hours. We didn't have a lab with it. But later that evening, I found a lab and I recorded that also on Screencast-O-Matic. Now, I didn't put it out there on Zoom because I didn't know I was going to find it and I couldn't give y'all enough warning to get it there. So anyway, the lab 2, and it's a really simple lab. So all you have to do, huh?
You say lab 2.
Yeah, we did lab 0 that first day of class when I wasn't there. And then we did lab 1, the, what was it? Last Thursday, maybe? What's that?
The last class meeting.
Yeah, we did lab 1, which was a long, long lab. I can't remember. Were you there for that one?
Yeah, that was our last time we met in class.
Right, yeah. And yeah, you turned in the lab and everything. For those who did the lab but didn't turn it in, I guess you're going to have to, you can either mail it to me, but really cheaper than that would be, but it's going to be a pain in the neck, is to scan it and send it to me, either through, probably through email. I haven't done the stuff on Blackboard yet. I'm not even sure if it works or how it works. I'm sure it must because I've been doing online classes. Other people have. But I can't tell you how to do that. So they say that the directions are out there under quick link on the web page, the main web page for the college. You know, there's a series of blue tabs at the top. Then there's one big gold tab that says quick links. And somewhere on there it's supposed to tell you how to do send things through Blackboard. But I think they got so many things out there, I don't know that one. But I do know that if you scan it and send it to me on an email, I'll get it that way. If you don't have any way to scan, then I would say probably put it in an envelope and mail it. But that's going to be fairly, not super expensive, but you know, it's not going to be trivial. And you'll have to go to a post office to do it, and I'd hate for you to have to do that. But if you know, whereas if you can scan it. And frankly, your telephones, a lot of your smartphones will scan, and if you can scan it with that and send it to me via email, that would be great. Okay? Now, yes.
I attempted to do the lab, but I sent you an email to let you know I received an error message. It won't allow me to, I think it's Moving Man.
The moving man, you couldn't get into it?
No, sir.
You went to Blackboard.
Yes.
Okay? Because I've gone to Blackboard a couple of times. Of course, I'm on the instructor side. I don't see the student side. You saw the, whatever it called, simulations, physics, or just laboratory simulations. You saw that.
And I attempted to download it, but in an error message as if I had to have another app.
Oh. Well, can you figure out how to get that, either driver or app or whatever it is? A lot of times those you can do electronically. I don't think you have to pay for them, but you just have to load them. I don't know enough about it to tell you how to do that, but I was hoping y'all would be more computer literate than I am. I know you are, but whether you can do that. See if you can figure that out, and if not, email your problem to Miss Jamie Glass. That's J Glass, Glass, just J, the letter J, Glass, no caps or anything, at lawsonstate.edu. She might be able to help you figure out how to do that. She can actually, if you allow her to do so, she can get into your computer, I think, and manage things. Now, I know she can do that on campus. She may not be able to do it from home, and with you being at home. But she is just an amazing person on the internet or on all things electronic. So if you want to give her a question on that, she might be able to help. I can't because, what's that?
Spell her first name, please.
I can't hear. Say it one more time.
Spell her first name, please.
Her first name is Jamie, Jamie, but
Okay.
her email address is just jglass, J as in Jamie, GLASS @lawsonstate.edu.
Thank you.
She's great, and she usually gets back really quickly too. Okay. Any other issues? Okay. Just an idea of what we're doing today. We are in chapter 2. We made pretty good progress last time in chapter 2. We're on page 48. The section number here is 2.7, but that's not very obvious. We're on page 48. We're going to do examples 214 and 215, and then we're going to move into impulse. 214 and 215 deal with conservation of momentum. So we're going to do those two, do impulse, do Newton's law of gravitation, Earth satellites, weightlessness. There's not much to do with that, and we'll be through with chapter 2. Now, I don't quite have it ready to send to you yet, but I will hopefully be sending maybe before the day's over, your chapter 2 test. Now, it's mostly multiple choice, and there may be a few calculations to fill in the blank. Nothing like the first test. The first test was mostly calculations and filling in the blanks with a few multiple choice. This is mostly multiple choice with a few. Also okay, so I'll be sending you that sometime after class is over with, because my wife is either going to her office to scan it, or we're going to set up the scanner at home, or she's going to do it through her telephone, one or the other. She has a better telephone than I do, smartphone than I do, and but still we couldn't get a great picture before, so we'll find some way to get it done. If not today, possibly tomorrow. I think she may be going into the office tomorrow just real quickly, and she may do her scanning then. Do it online? What's that?
We're just taking the test online?
You'll just take the test and then return it to me either by email or however. Well, I'm going to do here's what I'm going to try to do. I've never done it on this new Blackboard. I'm going to try to email you through Blackboard and attach the test to the email. This new Blackboard, this Ultra, nothing seems to work as well as what it did on the old, so I can't guarantee it'll work. If it doesn't, then I'll have to email you all in person. I'll have to type in all your emails. That's going to be a pain in the neck, so I'm hoping it'll work through Blackboard. We'll see.
We need to do it immediately after class?
What's that again?
We need to do it immediately after class, or just sometime by the end of the day, by the end of the week?
Okay, when do you have to return it to me? Is that the question?
Right.
Okay, I say you have a week to get it done. Now, next week is spring break week. I may be checking emails, but I may not be where I can print them or anything. So, actually it'll be 2 weeks from today because spring break week is in there. But most other tests you'll have a week to do. Same thing with the labs. Try to get them done within a week. Now, if you have a problem like Cash is having, yeah, I understand that, and get the problem situated, taken care of, and do it. Now, I'm going to be doing another lab today, and this is also at that same site, but hopefully, Cash, you'll be able to do the second one. It's done by somebody differently, but it may be using the same driver. I don't know. I don't know how they set these things up. These came from Dr. Bryant, and I'm just using the ones that he had out there. And these are pretty lame labs, but that's all I can come up with at the moment. Did anyone else look at the lab? The lab 2? Okay, try. Yeah, you can see it through the YouTube video and then try to get it done that way. I put another announcement out on Blackboard that I had done the video, and the title of it is just, I think, this PHS112 Lab 2 or something like that. I don't remember how I named it. Okay. Yeah, no, the first one was Moving Man. This one will be Ladybug Two-Dimensional Motion or something like that. It's, like I said, they're pretty lame. But listen up to what I say to do to the lab, and that's what you're to turn in. Once you do it, you capture the screen, print it, and then on the back of that paper, answer the question that I told you. The last one was just pretty simple, just one or two, I can't remember how many questions, but I explained it all in the lab. And this one will have maybe a couple more questions in it. Once I have more time to work on these, I'll type up the questions so you'll know exactly what, and then I'll send those to you for when you watch the lab. Then you print off your result and then answer these questions. And you can send that back to me then. I didn't have time last night because I was teaching until after 6:30 last night, and I found the lab, but I didn't have time to write questions, but I'll tell you what those questions are. All right, so we'll finish chapter 2 today, and later I'll send you the test when I can get it scanned. That may be tomorrow. You have 1 week from the time you get it. Most times, this time it will be 2 weeks because of spring break. But once we finish chapter 2, we'll go on and get started in chapter 3. And we'll work in chapter 3 until we run out of time, and then I'll go over the lab with you. Okay? I'll go over both labs if you need more emphasis on that first lab. We'll go over both of those, and you can watch me do what I do, and then you'll need to do something similar. You get to be creative, do whatever you want to with it, but you just have to answer the questions that I'll be telling you what to answer. So, we'll finish chapter 2. Later, I'll send you a test on chapter 2. We'll start chapter 3. When we run out of time, which will be at 3:45, then we'll stop the class, and then I'll take you to the lab and show you how to do the lab and tell you what questions to answer, and then anything. Any questions on any of that? No?
No, sir.
Okay. Has any new person that I haven't called a name for yet come aboard? So far I have Jack. Say again? One more time. Harris? Perrin. Gotcha. All right. Yeah, you were here last time. Okay, let me go over quickly who I've got. I've got Jacob Dove, Sam, Gunnar, Jeff, Edward, Jason, Ian, Zane, Jose, Perrin, Cash, and Chad. Anyone I'm missing? Say again? I couldn't hear. Okay. Kurt Jones, right? Okay, got you. I thought you would be back because you were here last time. All right. Anybody else?
Joshua Matthewson.
Oh, okay. Josh is here. All right. Now, Tiffany was here last time. Is she here today?
No, but Tasha is.
Okay. Tasha's here. Good. Tasha Harper, right?
Yes.
Okay. I thought at first you said Kasha, and I said, I already got Cash here. Okay. All right. Got it. Anyone else? Okay. Now, if any of you came in after I was talking, you'll need to go back and listen to the YouTube video, but we'll do whatever I was talking about. But anytime you have questions, please ask. I can't see you raise your hand, so just ask if you got questions. I'll stop wherever I am and see if I can answer them. Okay? All right, now, we were doing conservation of momentum. This is on page 48 on in chapter 2. The section in chapter 2 is 2.7 momentum, and let me just see if there's a slide here. Yeah, here's a good place for it. Example 214, bottom of the left-hand column on page 48, and it goes over onto the right-hand column. So here's what we have. A 20,000 kilogram railroad car. What's that a measure of? Ooh, let me get my pen set up. Wait.
It's a measure of weight, isn't it?
No. Pounds would be weight. Kilogram measures mass. Okay. So the mass of the railroad car, I'm going to call this car A. There's a reason for it. There's going to be a second car. Now, I'll tell you this too. Yesterday and today, periodically my pen quits writing and then writes over itself and draws lines all over the place. I can't control it. So if it's really ugly, just ask me what I just did. That's supposed to be car A. The mass of car A is 20,000 kilograms. Okay. And this car A is coasting at 3 meters per second. So what is 3 meters per second a measure of? Say again? I thought someone said something. 3 meters per second. Is what?
Time.
A little louder.
Time.
No, meters per second, not just seconds. 3 meters per second. Okay, I'm going to give you a hint. Say again?
Distance.
Meters per second.
Acceleration.
Not acceleration. That would be meters per second squared. Meters per second is a lot like miles per hour, huh?
Velocity.
Yes, that's velocity. That's your velocity. 3 meters per second. Now, I'm going to draw an ugly little picture here. Okay, here's the box. The box car, railroad box car. Really ugly picture here. Okay. Okay, here's the connectors here. And this one's moving. It has a mass of 20,000 kilograms. And again, my pen doesn't write well for some reason. Okay, this is boxcar A. Okay, this is the mass of car A. Okay, and it is moving with a very slow velocity. It's coasting with V. This is for boxcar A. Is 3 meters per second. Okay, here is boxcar B. Okay, that's a, shouldn't be any bigger. Should be the same size because it collides and couples with. There's a coupler there. And a second identical car at rest. Now, if it's identical, that means that we'll call it B here. That means the mass of B is also 20,000 kilograms. Okay? That's also a mass, 20,000 kilograms. But this one's at rest. Okay, what does that mean?
It's not moving.
Yes, its initial velocity is 0. This is for car B. Initial velocity for car A is 3 meters per second. Okay, get out of there, spaceman. Okay. Now, there's the train tracks here. Ooh, it should be under the wheels. Okay, something like that. Okay. Now, flat level ground, all that kind of stuff. What's the resulting speed after the two cars collide and couple? Because it says they collide and couple with the second car. That means they fasten together. What do you think is going to happen?
Speed's cut by half.
Say that a little louder.
Speed's cut in half.
Hey, you're really good. They couple together and then they move together, and as you said, the speed will be half. Why? Because we doubled the mass. And here is the formula for momentum, linear momentum. So linear momentum of car A initially was 20,000 kilograms, and the pen is not writing well, times 3 meters per second, that's the velocity, okay? And it's not writing well at all, okay? That would be how much? 60,000. And unfortunately, momentum doesn't have its own unit. We have to name it kilogram meter per second. Awkward thing. Newton is a kilogram meter squared, meter per second squared. That's a force. Momentum doesn't have its own name. Okay, so we call it kilogram meter per second. There is another name for it too, but it's still a compound name. So that's the initial momentum of car A. What's the initial momentum of car B? 0, because its velocity is 0. Absolutely. So what's the initial momentum of the system of both cars?
30,000.
Yes, 60,000. It would all be in car A. The system would be 60,000 kilogram meter per second. Okay? That's the initial momentum of the system. After they collide, okay, because, I'm going to go to another slide here, momentum is always conserved. That means the total momentum of a group of interacting objects remains the same in the absence of external forces. We're going to assume there are none. Then the total momentum at the end is the total momentum at the beginning, and vice versa. So, if we know the initial momentum's that, we know this is also the final momentum of the system. Okay? Well, what is the new system? The new system, after they collide, what is the mass of that system? 40,000, because you add the two masses together. They collided and they connected. They linked together. That's kilogram. And what we're looking for now is the final velocity of the system. We know the final momentum, 60,000. We know the final mass, 40,000. So we're looking for the velocity, so we divide both sides by 40,000 kilograms. Divide this by 40,000 kilograms. Okay? Kilograms go out, and all these zeros go out, and 6 divided by 4 is the same as 3 divided by 2, which is 1.5 meters per second. That's your V final. And you hit it right on the nose when you said it's half the velocity it was before. You doubled the mass, you half the velocity. It was 3 meters per second, now 1.5 meters per second. Excellent. Does everybody see why that's the case? Now, yes.
Oh, I was just saying, yes, sir, I'm sorry.
Oh, okay, no problem. The book does something really stupid here, in my mind. They get 1.5 meters per second, but then they say, well, because you only have one significant digit in both of these, we're going to round that to 2 meters per second. Do not do that. That makes no sense. It's not 2 meters a second. It's make it 3 halves, and then you don't have to round anything. That's really ridiculous to say the final speed is 2. It can't be 2. It's going to be 1.5. But they just get carried away sometimes with their significant digits. Especially when you're that small in numbers, don't do it. Okay. Any questions on that? All right. If not, all right to erase this? Or is anyone still writing? Okay to erase?
Yes, sir.
All right. Now, 2.15. A student and her rowboat have a combined mass of 100.0 kilograms. This time they told you what it was. The mass, I'll just say student and boat, okay, is 100.0 kilograms. Now this time, how many significant digits do we have? 4, okay? When you just have a single digit there, that's all that's significant. When they put a decimal in like that, that makes all 4 of those digits significant, okay? Now, she's standing in the back of a motionless boat. Now, I don't draw boats very well, just any more than I drew rail cars, okay? But here she is standing in her boat, okay? Shouldn't be standing in the boat, but she is standing here in the boat, okay? And she tosses, oh, and by the way, it says a motionless boat. That's a really ugly boat, isn't it? Okay, never mind. Don't answer that question. Okay, so what does it mean by a motionless boat? Initial velocity is 0. And we know the mass of the student and the boat. She's there, okay? Standing in the back in the motionless boat in calm water, the water's not moving either. She tosses a 5.0 kilogram rock. So the mass of the rock is 5.0 kilograms. Now, how many significant digits are there? 2, only 2. So who cares if you got 100 to the 4, you only got 2 for the rock, okay? She tosses the rock out of the back of the boat. So I'm sorry, she's facing this way. Here's the back of the boat. We call that the stern, by the way. And she tosses the rock in this direction with a velocity. Velocity of the rock is equal to 5.0 meters per second. How many significant digits there? Also 2. Now, what's going to happen? If she throws that rock out of the stern of the boat at 5 meters per second, is the boat going to do anything? Okay. Let's think about this. What's the initial momentum of the system? She's standing there holding the rock. 0. So initial momentum of the system is 0. Okay? Now she throws the rock out the stern of the boat. It has a mass, it has a velocity. What is the final momentum of the rock? It's what? 10. I can't hear. 10. No, you're multiplying, not adding. It's mass of the rock times the velocity of the rock. 25. That would be 25, and you don't have to put a 0.0 after that one, and that's kilogram meter per second. Now, I put that as going in a positive direction, so we'll call that a positive momentum. So what must be the momentum of the student in her boat now? Well, what's the final momentum of the system? Momentum is conserved. The final momentum, total momentum at the end is the same as it was at the beginning. So what was the final momentum of the system? It's also 0. Because it can't. You can't gain momentum without losing momentum, okay? So she must have some momentum. What do you think her momentum would be? She in the boat. If the rock is going at 25 to the right, What must be her momentum? Any ideas? Say again? You have to add to 0. So that would be minus 25 kilogram meter per second. Okay? Well, what is the formula for final momentum? Any ideas? Okay. The mass of the student and boat times the velocity of the student and boat. And that's what we're looking for. The question was here, I forgot to write it down, what will be the resulting mass speed of the boat with the student in it? Hopefully she didn't fall out, but she was standing in it, she may have. So this is what we're looking for. Do we know the mass of the student and boat? Yeah, 100. So what we'll do, the final velocity of the student and boat, this is the final one, is equal to the total momentum, negative 25 kilogram meter per second, divided by the mass, which is 100.0 kilogram. Kilograms go out, and that would be negative 0.25 meters per second. So creeping along there ever so slowly at 0.25, a quarter of a meter per second. She is moving, hopefully, toward shore, because I think what happened, she lost her paddle. No, well, no, we don't know that. Okay, and that is the answer they have in the book. They don't put the minus sign there. They just said, because they're saying speed. Velocity would be a direction quantity with a minus sign. They're saying what's the speed. Speed is the magnitude of velocity. Does that make sense? Yay or nay?
Yay.
All right. Yay. Okay, we got a cheerleader here. Okay. All right. That's conservation of momentum. Now let's move on to impulse. Okay. Any of you ever play, say, tennis, baseball, any of those sports that you hit things with? Golf? Any of you? Okay, basketball, okay. It kind of works for basketball too, but I'm thinking of those sports that you hit the object with something, like a bat, a racket.
He said racquetball.
Racquetball, yeah, that would do it. Now, they say here, have you ever heard that you should follow through when hitting a ball? If you really want it to go very far, you better. And here's why follow through is important. When you follow through, the bat or whatever you're using is in contact with the ball for a longer period of time. And the force of the hit with the ball is going for a longer, okay? Because the effect on the ball depends not only on how hard you hit it, but how long you hit it, okay? And that leads to this concept of impulse. It's a force acting on an object over some time period. So how I'm going to write that down, let's see if they write it down here, okay? Well, not quite. Let me write it down here. Impulse. This is in your book if you got it open to page 48. Impulse is equal to the... Okay, I don't know if that's someone saying something or just some noise. Force times a time period. That's what it's saying here. Force acting over some time. Now, you could call that time a delta t if you wanted to, because it's a time period. I think we just added somebody to the class. Yeah, I've got 18 participants now. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So either 2 or 3 more people must have added. Did anyone else add since I called roll? Anyone?
Me, Jacob Forte.
Who's that?
I moved you called roll when I got in. Jacob Forte.
Okay. Yeah, there you are, Jacob Forte. Got it. Anyone else? Okay, I still don't have Drew Allen, Carpri Betts, Lydia Caddis or Cameron Danzy, Brianna Davis, Kaya Dudley, Eric Hill, Zach Hogue, Emily Jordan, Mrs. Lewis, David Nash, Anaya Nunn, or Tiffany Silcox. Is anyone there that I called the name but as being absent, but you're really there? Okay. Must be somebody because it was listing 15 and I only add up to something like 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Well, maybe so. All right. So that's what impulse is. Force acting over a time period. Now, we mentioned hitting a ball with a bat. Now, are any of you baseball, even if you don't play baseball, you like watching baseball at all? Okay, I've just got that we have 17 participants. Did anyone else just add? Yeah, I think that's all, because I think I'm a participant. Okay. All right. Any of you know anything about baseball? Even a little bit? Yeah. Okay. Now, those big hitters that are going for the fences, I guarantee you they're following through. They keep the bat on the ball as long as necessary, okay? As long as they can possibly do so. And they will send the ball flying a lot further. But every now and then, with either 0 or 1 out, and a man reaches first base, sometimes the next batter, especially if they're not all that great of a batter, maybe the pitcher or somebody like that, they may do something to advance the runner. What is that action called? Bunting, exactly. Now describe to me how you would bunt a ball.
You hold the bat in one spot till the ball hits it.
Okay, and then sometimes you actually pull the bat away from the ball to keep it from going too far, right? Because you want it just to dribble down, say, about halfway between home plate and first or home plate and third, because you want to get it as far away from any of the fielders as possible, right? So sometimes they actually yank back on the thing. What they're doing there is hitting the ball, and the ball may be a fastball, it may be coming in quite fast, but then when you pull the ball back, the bat back, that keeps it from doing for a longer time period. So your impulse then is very small, even though the initial force may have been pretty high with a fastball, but the time period is very, very small. Does that make sense?
Yes.
Okay. On the other hand, if you follow through like you're supposed to, watch Serena Williams play tennis sometime. She smacks that ball with a lot of force, but she keeps that racket on the ball a long time. Unless, of course, she's trying to just do a drop shot right over the net. And then she'll yank back on that. She'll hit that ball very softly and not keep it in touch with the racket very long. Any of you golfers? Or at least watch golf? When you're driving that ball, boy, you take a big old swing and you want the head of that driver to stay on that ball as long as you can leave it there. I mean, you swing that thing and hope that it stays. However, when you're putting, especially a very short putt, do you swing that putter? I hope not, okay? And sometimes they just barely tap it and bring it right back, because you want the time period to be very short then, so the impulse would be pretty significant. Okay? I mean, very small. Okay. So that's the one side of it. On the other side of it, an impulse produces a change of momentum. So we have an impulse up here, and my thing is in the way now, so I'll write it down here. Impulse, well, it's not writing now. Okay, impulse, now it's moving out of the way, is equal force times this time period. Okay, if I could get it to write. Or an impulse is also an impulse produces or is equal to a change in momentum. Remember, what is momentum? Someone remind me. I started to write it. What is momentum? Mass times, no, velocity. Mass times velocity. We're just working at that, remember? That's a change of momentum. My pen is not writing very well, okay? It produces a change of momentum. That's what the second thing says. Change is the delta, difference in, okay? Now, if you put these two together, you have that a force over a time period is equal to a change in momentum, okay? That's an equation for impulse. Both of those equals impulse. Now I'm going to do something a little bizarre here. And remember, this could be a delta t. The time interval is a delta t. So I'm going to divide both sides by delta t. Divide both sides by delta t. If my pen would write, this would make more sense. There we go. And the dividing line didn't show up. There it is. So the delta t's go out over here, if I could get them to leave. And now, when you have a change of momentum, it's usually always caused by a change of velocity, because hopefully you're not changing any mass. Now, of course, if you hit the cover off the ball, yeah, you lost some mass, but no one really does that. That's just a saying. So you could pull the mass outside of the delta and then have delta V over delta T. Now, does anyone remember what delta V over delta T is? That delta didn't come out too well, did it? Okay, there we go. Anyone remember what change of velocity over change of time is? Anyone? Velocity over time. Miles per hour per second. 0 to 60 in, whose was it? That was that Jacob's car that could do it in 2 seconds? Or truck, or I don't know, I don't remember. Okay, that was acceleration. Change of velocity over change of time is acceleration. Well, guess what this is? Mass times acceleration. That's Newton's second law. Force equal mass times acceleration. Okay? And in fact, it's my guess that Newton expressed it this way. A force creates a time rate of change of what he called his quantity of motion, mass times velocity. I don't think he called it momentum. I don't know. He wrote in Latin. I don't read Latin, so I have no idea if he called it that, but that's my guess. The time rate of change of momentum. Okay? We say mass times acceleration. I think it was force is equal time rate of change of momentum. Now, a few sort of practical examples of this. Y'all are all very young, and I remember when I was very young, younger than you, the earliest cars, in fact, it was the first car I ever remember my father owning. He always had owned pickup trucks before that, but our family was getting a bit too big for a pickup truck because they didn't have club cabs back then. So anyway, the first car that I remember he bought, it was a Seems like it was a Plymouth, but I don't remember what kind it was, what the brand name. They don't even make Plymouths anymore. But anyway, it had a nice hard metal dashboard that for some reason poked out at you. It came out and curved back in. Just a perfect thing to wham into if you ever had an accident. In fact, they used to call back in those days the passenger seat the death seat, because back then there was no such thing as airbags, no such thing as seat belts. You had yourself and a hard metal dashboard. And if you were to ever to hit something, a tree, an embankment, or anything else like that, if that passenger was sitting there, he and that dashboard, hard metal dashboard, are going to collide. Now, let's just say you were going at 60 miles an hour. That's pretty fast, okay? And you hit something and you come to a complete stop, okay, because you hit something that's immovable, okay? Well, you have an enormous change of momentum then, because your force is still pretty large. Well, your change of momentum, your velocity went from 60 to 0 in a very quick time. The mass of that car is very big. The time period is very small. The force is going to be enormous. Absolutely enormous. Okay? Now, it seems like it was the next car we owned. Didn't have that big metal dashboard there. They had a little bit of padding. I'm guessing less than an inch of padding on that dashboard. Probably was still metal under there, but at least then, if you hit the dashboard, the time interval was not like that. The time interval took just a little longer, maybe a tenth of a second or so. Originally, that was less than a thousandth of a second, perhaps. Well, if it took a tenth of a second, then your time period was much bigger. Same change of momentum. Your car is going the same mass of car, same velocity of the car. Everything's the same except the time period. If it went from a thousandth of a second to a tenth of a second, okay, for that to mash and come back out, what have you just done? You decreased the force by 100 times. You probably are still going to have some pretty serious injuries, but it may not be instant death, okay? Now, later than that, they had other improvements. And the first I remember was the seat belt. Now, and it was just a belt then. And what the seat belt did was hold you in place so that when you did move toward the dashboard, it took you a lot longer to get there. Now, you didn't have a shoulder harness. It was just a seat belt. So you still went forward, and you might wind up connecting with the dashboard. But because the seat belt was holding you back, that may have taken a second or two, or maybe even not 10 seconds, but it took a bit longer. Now you've decreased the force even more. Okay? After that, they came out with the shoulder belts as well. At first, they were separate, by the way. Nowadays, they're all in one. And that holds you back even longer and better because your body doesn't go forward. And it takes a long time. If it was a serious enough accident, you may still hit the dashboard, but it's going to be a lot longer, meaning the force of you hitting that dashboard is much less. And now they have airbags. And what the airbag does, it deploys, and now I don't think you ever touch the dashboard at all, because that takes a certain amount of time to compress before you'd even reach the dashboard. So you escape most of the time, hopefully, with very small force. You may get some scratches, some bruising, a little bit of stuff like that, but it's not nearly as serious as before. The longer that time interval before you make impact, the less the force is. As long as that momentum's the same. And it would be. If you're going 0 to 60 or 60 to 0, that change of velocity is the same. Your mass of the car is the same. Everything's the same. So you're going to have a significantly lower force if you can significantly increase that time period. Okay. Did I beat that into the ground? All right. The same thing works. Padding for elbows and knees. Big controversy these days in football about concussions and things like that. So many players are showing up with some pretty lifelong issues of too many concussions. So they are trying their best to improve the padding on the helmets, and absorbing, making the time interval between the time you get hit and your head hits something that's immovable, increasing the padding and the time period there. Same thing for elbows, knee pads, shoulder pads. They all work in the same principle. You're increasing the time period before that change occurs. We call it cushioning, and that's what it's doing. All it's doing is increasing that time period. Okay? I can remember back when they had concrete objects there to stop people from going into the median, say. Well, that caused a lot of issues. Nowadays, then they went to metal things, but they had a little bit of a cushion behind the metal. You may have seen they set away from the post, and there's rubber material in between. And nowadays, they do things like barrels or even those wires. You've seen those along the interstate, haven't you? Strung between those little posts they have there. Those wires will stretch and make those posts collapse. There's less thing. Your time period over which you're forced to stop is being increased, but still keeping you out of the median or the other lane. So, and then of course they say plastic barrels on the highway, much safer than concrete pylons sitting on the highway. And I can remember they used to use those. Now this is a little more, perhaps morbid example. Have you ever, and coming up, I don't know if it's going to happen this summer or not with the virus going around, but Summer Olympics were supposed to be this summer in Japan. And I don't know if y'all watched most of them, many of them, but one of the events was always your track and field and gymnastics and those kind of things. And let's think about, let's take track and field for a moment. Let's think about those high jumps and then maybe pole vaults. Those people are coming from some pretty high heights, pole vaults even higher than they. What did they land into? The ground? The pavement? Anyone ever notice?
It's a cushion.
Yes, a blown up or layers of cushion all over the place. Let's go indoors and see the gymnast. And sure enough, when they're doing the high bars, just about any of their events, even the floors when they're doing the floor event, notice they have it built up and it springs for them, because when they land on it, that gives them an increased time period before they stop, decreasing the force on their knees, their ankles, and whatever other body parts. Now, y'all were probably too young to remember this, but back in 1996, Atlanta hosted the Summer Olympics. And I believe it was that Olympics, there was a little Chinese gymnast, and I don't mean that in a diminutive type way. Those Chinese gymnasts, they looked more like young girls than they did teenagers. And people swore they were doing things to them, either treating them with chemicals or cheating on the birth dates, because it seemed like the younger the child, the more they could do some of these things, some of these really complicated things. They had this one gal who went racing down what they call the vault, racing down this runway that they had there. She hit a springboard, and then she went up over a pommel horse, and she was doing twisting and turning and gyrations and all, and one of those last gyrations she sort of missed on, and when she did, I think she missed the pommel horse, and that was good. She wound up not landing on all those cushions, but landing on the hardwood floor. Multiple breaks in her neck, her back. As far as I know, she's a quadriplegic to today. Why? That floor, the time period for that fall was almost instantaneous. Thousandths of a second or something like that. The force, enormous. Same change of momentum because her mass was the same, her velocity was the same. But when she would land on or anyone would land on all those cushions, then that took longer for that stop to happen. The time period increased big time, the force much less. So yes, it makes a big difference. Okay, that's impulse. I thought there was an example of it, but they don't give any. So let's move on to forces and circular motion. This is 2.8. This is over there on page 49. There is a little concepts applied, and this would have been one of the upcoming labs. The lab after today's lab would have been one similar to this, not quite the same, but similar to it. Have you seen that? Those balls hanging from sort of in a V from two parallel beams, you might say, and you pick up one ball and drop it. There's 5 balls there. They're all touching each other. You pick up one and drop it, and one on the other end goes up. It comes back and hits, and you pick up 2 and 2 pick up and go. You pick up 3, and even though there's only 5 balls, the third ball continues with the other 2 on the other end. You know what I'm talking about? Have you seen that? I take it not. Okay. Anyway, see if you can find one. Look at it, play with it while it's pretty incredible. What is that illustrating? The conservation of momentum. Okay? There are other conservations involved, but that's the main one. All right, so now we're moving to 2.8 on the right-hand column of 49. This is forces and circular motion. Now, circular motion, if you are ever moving through a curve in circular motion, I guarantee you're accelerating. Why are you accelerating? What does acceleration mean? Anyone remember? What is it?
Velocity.
Change in velocity. And velocity is what kind of a quantity? Scalar or vector? It's a vector quantity. What does that mean? Direction matters. Okay? If you're changing direction, you're changing your velocity, even if your speed is the same. So if you're going around a curve, guarantee your velocity is changing. Even if your speed is not changing, your velocity is, because the direction is changing. If the direction is changing, you're accelerating. You may not be increasing in speed, but you're still accelerating, because acceleration is a change in velocity, even if it's just a change in direction. This kind of acceleration is called centripetal acceleration. Okay? What this word, if you look at the first 5 letters of centripetal, what word do you almost see in there? You're missing one letter. Center. That means center seeking. Centripetal acceleration is always going toward the center of the circle. That's what centripetal acceleration means. A centripetal force has to be acting. Now, I've got a message up there saying my internet is unstable. Did it sound like I was cracking up or something?
Yeah, you were, but it's better now.
Yeah, it's better now. It went off. That's been happening today some. I don't know if it's because my wife's downstairs working on her internet and maybe using most of the bandwidth, or else we're just getting a bad signal today. I don't know why. My Wi-Fi is downstairs, but she kicked me out of downstairs because I made too much noise last Tuesday. Okay, So anyway, centripetal force must be acting because what is the force? Mass times acceleration. So even if there's no change of velocity, change of speed, if you're turning around a circle, you're changing direction, so therefore you have a centripetal acceleration, therefore you have a centripetal force. Now, they give this, say that again?
Would this be a better example of golf?
I couldn't understand that. Was that directed at me?
Yes.
What were you saying?
Would this be a better example of golf?
A better example would be golf? Is that what you said?
Would this be a better example of golf?
Of football? I couldn't understand.
Golf.
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 Yeah. Let's see. There is a sense that it is. When you're swinging that club, most of the mass of that club is at the head, right?
Yes.
So when you're swinging that club, if you were to lose your grip, watch out, fans, because that club's going to head off in a constant direction. So your grip on the club is what's keeping that club from flying out of your hand. So in that sense, yeah, it is a pretty good example of that. They use the term here centrifugal force, and you hear people talk about that. There really is no such thing as centrifugal force. It's an apparent force. It's just like when you're on that bus and it makes a sudden turn and you feel like you're thrown into the wall, into the side of the bus. No, you're not. The bus cut in front of you. You feel like you're thrown. You're not. That's because the bus cut in front of you. You're trying to maintain your momentum, your inertia in that same direction. That's what centrifugal force is, what they call that. That's the apparent outward tug when the direction changes. It really isn't. You're trying to maintain your momentum, your inertia. It's that you have here's one example. And since a lot of you are guys, I bet you sometime or another in your youth or childhood, you tied a rock to the end of a string and swung it around your head or something sort of foolish like that. Yes or no?
You catch them.
Yeah, I believe so. Okay. And what you're doing, that string is exerting the force on that rock as it's spinning around your head. But if you ever let it slip out of your fingers, or the string broke, or you didn't tie it in there very well and the rock took off, it always went to a window, didn't it? It never seemed to fail to hit a window. But anyway, that centrifugal force, what they were calling that, is really the force of the string pulling on you, not the force of the rock trying to get away. Okay? It is a centripetal force that's always moving toward the center. When that centripetal force ends, you no longer are holding on to that string, that rock takes off in a straight line motion. That's where it was trying to go all along. So here's the illustration, supposedly, of that. Oh, there it is. Boy, that was slow coming up. Okay? If you're swinging that rock around, and here's your string, there's the center, that's where your hand is holding it, swing it around like that. It won't stay on this page here. The centripetal force is always pulling the rock toward the center. Center seeking. The velocity of that rock is always tangent to that circle, but because that centripetal acceleration is pulling it inward, then it moves in a circular pattern. Velocity, though, is always tangent. Okay? Now, let's see if they give us a formula. No, they don't. And my internet connection is unstable again. I'm going to wait till it stabilizes. Okay, hopefully it's better. Here are the two formulas that we use for this. For acceleration, the centripetal acceleration, A sub c, if my pen would write, is equal to V squared. If I could get the pen to write here, it's not even, I think it has to do with the internet being unstable, because I cannot get the pen to write. Now you would think, oh, there it is. V squared over R. The pen won't write. There it is. V squared over R. That's your centripetal acceleration. Now, if you, I'm sure you were paying close attention early on, I said most of the time if you have seems like we've lost somebody. It's down to 16 participants. You didn't know this, told them you did it. Okay. Not you, you're still there. The other guy. Okay. I said that most of the time if your variable is squared, it's going to be preceded by something over 2. 1/2, 3/2, something like that. This is the one place where that's not the case. Your V squared doesn't have a 1/2 in front. But that R sort of takes the place of that because R is also a variable in a sense too. Let's look at the units and see if they make sense. What is typical unit? Let's use SI unit for velocity. What would that be? You can use US customary if you want to. Typical units for velocity. Somebody, anybody. All of you fallen asleep already, huh? I do that. Oh, someone just snored. Okay, no. Huh?
Speed? Question mark?
Okay.
I'm sorry.
It's the units for velocity. Typical units. How about meters? I can't get it to write. Again, my pen is screwing up here. That dot just goes wherever it wants to. Huh?
Seconds.
Meters per second. You're absolutely right, but I can't write it. I keep trying to. You see the, there we go. Meters per second. And now it's writing several times. Okay, meters per second. But we're squaring that. I can't square it either. Okay, there's one parenthesis, there's another one, or at least part of one. I don't know what's going on here. But anyway, you're squaring it. I can't write my 2 either. There's that parenthesis is now finally growing, and that's supposed to be a 2. Divide that by, what's a good unit for radius? What do we measure radius in? Anybody? We measure radius in lengths. And if we're using meter per second, can't get my pen to write. My whole thing disappeared. Meters per second squared. And then this would be meters. Well, this would be, if I could get it to write, it's hardly worth it anymore. Okay? This would be meters. Meters. I can't get it to write. You see that little dot that moves around? That's supposed to be my pen writing, but it just is not connecting. Finally, yesterday, I had to, that would be meters squared per second squared, because if you square that, you square both of the units. I can't get the second to write. And let's try the square. There, it wrote. Divide that by meters. Oh, that wrote fine. This meter, I'm trying to get it to cancel out, but it won't. That meter cancels one of those meters. And that gives you it would help if you could see it. There we go. Now it's completely gone. It wipes out one of these meters. All right, that did. And that leaves you with the unit of Okay, there's one piece of the equal sign. One more. Okay, there we go. Meters per second squared. Okay. I don't know why it's writing like this. Meters per second squared. That's a good unit for acceleration. Meters per second squared. Okay. And now for some reason the R disappeared. Okay. I don't know what's going on here. So that's centripetal acceleration. Well, how do you get centripetal force? Force is okay, somewhere there is going to be an F. Centripetal force is equal to mass times centripetal acceleration, which is mv squared over. Can't get my dividing line to right. You see the ball move? Ah, there it goes. Per divided by radius. And now the radius. It'll make a mark down here, but it won't make it here. There's an R under there, if you could just see it. Okay. This is absolutely nuts. There's the R. mv squared over R. Well, it was there and then it disappeared. There we go. It came back. mv squared over R. That's the centripetal force. All right. There are a couple of examples here. This could be nauseating trying to get these to work. Let's try it. Okay. See if I can erase that scratch. There it goes. All right. Example 216, this is on page 50. A 0 point, now it's writing fine, 25 kilogram. It writes fine for a little bit and then starts doing weird things like that. And then I can't get my eraser to come up. Ah, I got it. Okay. 0.25 kilogram. Sometimes if I write really slowly, it will do better. Other times it doesn't seem to matter. Okay, kilogram ball. What's that a measure of? Mass, that's it. Now it won't write at all. I can't write a thing. Yeah, there's the equal sign, there's the mass, okay. Is attached to an end of a 0.5 meter string. 0.5 meter. What's that a measure of? You're going to take this string and swirl it around your head. What's that a measure of? Going to hold that ball in place. That's your radius. I can't get, no matter how slow I write, it is not going to write that R. Okay. Now this happened yesterday too. My pen is not responding at all. Okay. Oh, there it did. And all those marks I made on the bottom. This is a radius and you can't read that now. So I'm going to try to erase. I can't get it to come up. Here we go. Okay. Try to erase all these down here that it made, unfortunately. get my pen back. It won't come up now. There's the pen. All right. That's the radius. And moved in a horizontal circle at 2 meters per second. What's that a measure of? 2. I can't get the pen to write. I can't get it to respond. Okay, yuck. Okay. I cannot get the pen to come back. Here. Nope. Almost did. There, we got it. All right, let's try it one more time. 2, 2, point, it will not write. I am so sorry. I don't know what it's doing. .0, that's supposed to be a 0, folks. There's supposed to be a decimal there. Meters per second. What is that a measure of? Anybody? Speed. Okay. I'll call it velocity. Is that okay? Since they use the term V down here. Okay. That will be our velocity, or V. Okay. So, I'm not going to bother with erasing. What is the net force is needed to keep the ball in a circular path? So we're looking at net force, and that net force is going to be your centripetal force. What was that formula? I can't even get the pen to write. Oh, there it goes. What's the formula for centripetal force? We just had it. mv squared over r. Okay? And what's your mass? .25, if I could write, kilograms times velocity, 2.0, meters per second, but you've got to square that and divide all that by your radius of 0.5. meters. Okay, that's supposed to be an M. Whew. Please excuse my dear Aunt Sally says you exponentiate first. 4.0, 2 times 2 is 4, 2 squared is 4, but then you square the units as well, meter squared per second squared. Okay? So we've taken care of that, and this meter down here is going to wipe out one of those meters, and this gives you, well, 4 times 0.25, or 1/4, is going to be 1. 1 divided by a half, or 0.5, is 2. 2.0, what units? Kilogram meter per second squared. That is a newton, and that's a great unit for a force. 2.0, or they just call it 2 newtons. Ah, I see why. Only one significant digit there, so they just call it 2 newtons. Goodness gracious. Now, example 2.17, suppose you make the string in example 2 half as long. So you're now going to make this 0.25 meters. Okay? What force is now needed? So now, instead of 0.5, it's 0.25. So you still have the same numerator, 1 divided by 1/4. Now the nu is going to be 4 newtons. Okay? Now, because you have 2 digits here, they put the 0.0 here. Aren't they kind of crazy with their units? Okay. All right. Any questions on that? I'm sorry that example took so much time and effort because the pen wasn't right. Got it? All right, let's move on then to Newton's law of gravitation. If you throw a ball into the air, it's going to drop back again. Can't help it. It's going to do it every time. A basketball, a tennis ball, a golf ball, baseball, softball. Throw it into the air, it's going to come back down. Okay? Why? Gravity. Say again?
Gravity, what comes up must go down.
Exactly. Gravity is always an attractive force between all masses. No matter how small, how big, or whatever, it's always an attractive force between 2 or more masses. Okay? It's proportional to the product of the masses. So here goes that proportionality again. The force due to gravity, okay? Can't get my pen right again. It does well for a bit and then stops. It just will not write. Okay? The force due to gravity, internet connection is unstable. That must be it. Okay. This is equal to, okay? Or, I'm sorry, not equal to, proportional to. If I could get the eraser to come up now. Okay. Now we'll try to get the pen back up. All right. Is proportional to the product of the masses. M1, let's just assume it's a two-body system, times M2. Product of the masses. But it's inversely proportional to, meaning 1 over, I can't get there it is, the separation distance squared. We'll call that R squared. Okay. Now, what is proportionality constant? It is Newton's law, Newton's constant of gravitation. Take away the proportional sign and put your constant in there. Rather than K, we're going to use capital G. Okay? Now, that's my writing. Let's see how they do it. Well, they don't do it, do they? I thought they were going to give the formula there. They haven't. Okay? So let me back off. There's the formula. F is equal to G times the product of M1 times M2 over, they call it D squared, I call it R squared. Okay? That is the uniform law of gravitation, Newton's law of gravitation. Now, yeah, we're going to come to this a little bit later, explaining why G is equal to 9.8 meters per second squared. Not going to do it yet, but we're going to do it soon, okay? And we'll also talk about how this is related to centrifugal forces of orbital motion. That's coming up next. Okay, in fact, that slide you saw under here made it. Let's do example 218 first. Okay? The question is, what is the force? That's the unknown here. What is the force of gravitational attraction between two 60 kilogram students? So here's a 60.0 kilogram student. What's that a measure of? Anybody?
Mass.
That's the mass. And you got two of them. So this is mass 1, mass 2, .0 kilograms. Okay. Who are standing 1 meter apart. Well, that's the separation distance. What I used is R, they used is D. I'll go and put it R since I've written it here. And this is 1.00 meters. All right, there we have it. Okay. Well, let's see what it is. Oh, and by the way, up here, the gauge G is equal to 6.67. I can't get it to write. There we go. It writes on top of each other now. Times 10 to the negative 11. The units are newtons, meter squared per kilogram squared. Okay, and I'll show you why that's the case. This is going to be measured in meters, but you're squaring it, so that's meters squared, so that's going to cancel that part out. These are both kilograms, so that's kilogram times kilogram, that's kilogram squared, that'll cancel that out, and then you're left with newtons. So that's why G has those units. But I want you to notice what an incredibly small number G is. That's 0.0000000000667. That's an incredibly small number of newtons meter squared per kilogram squared. It just is incredibly small. Okay. So if you enter this into our formula here, your G is this very small number, 6.67. Find if I write really slowly, sometimes it will, right there it goes, finally caught up, times 10 to the minus 11 these units. Newton meter squared per kilogram squared. Okay? That number we're going to multiply, if it'll multiply, by, I'm going to write over here, 60, this is your mass times mass, 60.0 kilogram. Okay, that's the mass of one student. The mass of the second student was also 60.0 kilograms. All right, that's that part. If it was just right. That's, okay. 60.0, that's supposed to be a kilogram, okay, divided by 1.00 meter squared. I squared 1, you get 1, okay? Let's deal with the units first. These 2 kilograms here wipe out those 2 kilograms. This meter squared here wipes out that meter squared. And it leaves us with newtons. But how many newtons? 6.67. Now, if you have a graphing calculator, scientific calculator, anything like that, I don't know if you know how to use exponential notation. I'll tell you how. 6.67. Don't ever type times 10. What you hit instead is either the key that says EE. That's what most of them say now, the EE key. Some of the older calculators may have an EXP key. Both of those raise them to exponents, whichever one your calculator has, EE or EXP. And once you hit that, you'll see 2 other smaller blocks come up, and that's where you type in either the negative 11. Now when you do that negative there, that's not the subtraction key. The one that's next to the, ew, that's ugly. It wouldn't write, it wouldn't write, it wouldn't write. And then all of a sudden it wrote 3 times, 4 times. Minus 1, 1. Okay. So you do 6.67 EE or EXP. Now what I was going to say about that negation side, that's the one that's up there in a parentheses. If you see that minus sign in a parentheses, that's the one you use here. Do not use the subtraction key, which is over there with the addition and multiplication and division keys. Don't use that one. Use the one that is the subtraction key. Now, if you're using your telephones, you probably are going to have to enter the 11 first and then do that plus minus key. That changes the sign. So whatever you need to know how to use your calculator. So that's what you got. 6.67 EE or EXP minus 11, however you get there, times 60 times 60. Then you're dividing by 1, which we're not going to pay any attention to now. It's just dividing by 1, okay? And that should give you an incredibly small number. Let me see if I can find it here. There it is. 2.40 times 10 to the minus 7 newtons. That's a 0 there. Okay, that would be 0.0000000. No, I'm sorry. Yeah, that's right. 240. Incredibly small number. That would be the force of attraction between those 2 people. Are they going to feel that? No. A newton is small enough anyway, and if you have 2.410 millionths of a newton, you're not going to feel that at all. Okay. So that's what they get there. Now, this thing about why G is 9.8 meters per second squared, let's talk about that for a moment. We're going to have that in a problem coming up shortly, so I'm going to hold off on that for a bit, and let's move on to this. Okay, if I can get my pen to, okay. I want to erase that ink. There we go. So here we have the Earth down here, and above it, there at some distance, you have the Moon. Now, The moon follows what I was going to say is the scale on this, they've got the Earth probably a little too small, the moon a little too big, and the distance between them way too small, okay? But it's okay, just giving you the idea. Now, if the moon going around the Earth like that, if it wasn't for the Earth's gravitational force, the moon would just keep on going in a straight line. Newton's first law. Any object in motion stays in motion unless acted on by an unbalanced force, a straight line motion. Well, there is an unbalanced force here. This is gravity of the Earth pulling the moon toward it. Okay, so that makes the moon start falling to the Earth. But the moon does have a velocity here, so it falls in a circular pattern. And that's what we were talking about with centripetal force. That is the centripetal force, the Earth's gravitational pull on the moon, that keeps the moon in orbit about the Earth. And not just the moon, all of our satellites, all of our communication satellites, all of our GPS satellites, all of our communication satellites, all satellites are up there, that are up there, are being kept up there, are brought there from the Earth's gravitational force. Okay, so that's what that means, provides the centripetal force for orbital motion. If you take the Earth, replace it with the sun, take the moon and replace it with the Earth or any of the other planets, you have the same thing going on there. That's why the Earth revolves around the sun, because the sun's gravitational force keeps pulling it toward the sun. If it ever got bigger or out of balance, we might do all that we could to try to stop it, but I'm not sure we could do enough. Okay. We still haven't hit why G is equal to 9.8 meters per second squared. I think that's coming in example 219. Okay? Now, the placement of this in the text is a little awkward because they basically, figure 228 is talking about the decrease in the gravitational attraction of the Earth as you get further and further from the Earth, and that's because the R is increasing big time. Okay? But that's going to follow the topic called weightlessness that comes even later. So we'll hold off on that until we get to weightlessness. So let's go back to this, and we'll do example 219. All right. The surface of the Earth is approximately 6,400 kilometers from its center. That's a long distance, isn't it? So here is the Earth, supposedly round. The pen just quits doing round and starts doing other things. I'll try to correct that, but it's going to wipe out too much, I'm certain. It's a perfect right angle there. I couldn't draw that if I wanted to. And I can't get the pen back. There we go. Okay. Wow. I'm running out of energy fighting with this thing. Whew. Okay. This is a lousy looking Earth. Okay. Hopefully we're not in that bad a shape. This radius here is 6,400 kilometers from the center. So the radius here is 6,400. Now that's approximately, if it would write, but it's not writing. Kilometers. Yeah. We've got a problem here. We'll get to that in just a minute. Okay. 6,400. That's supposed to be another zero there. It just didn't show up. From its center. if the mass of the Earth, so this is the radius of the Earth, the mass of the Earth is equal to 6.0 times 10 to the 24 kilograms. What is the acceleration due to gravity g near the surface of the Earth? Okay, we know our formula. The force due to gravity is equal to g times m, and that will be the mass of the object, times the mass of the Earth. Mass of the Earth, to get it to right. Someone has a phone call coming in. Mass of the Earth divided by the radius squared. Okay. Now that's on this side. On the other side, this is the mass, force due to gravity, mass, won't write the M. I don't know why. It's having more trouble with M's than any other letter. I think it's because they changed directions, but I can't get my eraser to come up. Okay, let's try that M one more time. I'll try it really slowly this time. M. Nope. Okay, M, G. Okay, there we have it. Now this mass, that ugly M there, wipes out this mass because they're the same mass, the mass of the object. Okay, so G then would be the acceleration, the universal gravitational constant, 6.67 times 10 to the minus 11. Okay. Kilogram meter squared. I'm sorry, it's not kilogram meter, Newton meter squared. Can't read that anyway. Okay. This is so frustrating. Newton meter squared per kilogram squared. Okay. Wow. Okay. That's the G. The mass of the Earth we just had was 6.0 times 10 I think that's the 24th. I can't get the pen to write that too. Yeah, 10 to the 24th. Now my internet connection is unstable. Okay, let me see if it does better now. Yeah, 24th. That would be kilograms. K will not write. There it goes. Kilograms. Divided by this radius squared. Now there's where our problem comes. We need this in terms of meters, not kilometers. So that's going to be, would work it out for you, but it is taking so long to do anything. I'll just tell you, it's 6.4 somewhere there, 4, okay, times 10. So 6,000 would be times 10 to the third, but kilograms is 10 to the third again, so that would be 10 to the 6 meters. Okay. So it's 6.4 times 10 to the 6th meters. Goodness gracious. I may have to stop and take a break. This is just wearing me down. My eyes are stinging like crazy. I bet y'all taken breaks, haven't you? It's right at 3 o'clock. Let me get this problem finished and then we'll take a quick one. Going in at 3:45, but I'm going to need water or something. But this thing is squared. Okay. I hope someone has a graphing or a scientific calculator or something that they can do this. Let's deal with the units first. Okay. Well, first, this Newton is a kilogram meter per second squared. That's what a kilogram is. Okay? That's what a Newton is, I'm sorry. So one of these kilograms is going to wipe out that kilogram. The other kilogram is going to wipe out this kilogram. Okay? Now, here we have meters squared down here. I haven't squared the numbers, but I'm pretending I squared the units. That will wipe out this meter squared. Okay? And all we got left is meter per second squared, which is a good unit for acceleration. Okay? So the units are working well. Now let's deal with the numbers. Now I have a calculator here, so I'll punch them in at the same time you do. Now mine is a phone, and I've got to turn it sideways because I won't be able to do scientific notation otherwise. I get my phone to come on. I think my Wi-Fi must really be terrible. There we go. All right, finally got it on. Okay, 6.67, and on my this one here I don't think has, oh no, it's not e to the x. It's not, that's not the one. EE. Now on my phone, that's just to the left of the number 1. EE, and then we type in, on my phone I can't do negation in front, so I have to do the 11 and then change sign. That's just above the 8, the plus or minus sign. That makes it a minus 11. Okay, I'm going to take that and do times, okay, 6.0, so I'm just going to do 6, EE, 24, divided by 6.4 EE 6. I should have put that in parentheses. I really blew this. I'm going to have to start over. Sorry. Okay. Sorry about that. 6.67 EE 11 negative times 6 EE 24 divided by, now I open parentheses, okay, and that gives me, do a 6.4 EE 6 close parentheses squared. equal. And I get the number 9.77, which we're going to round to, I can't get my equal sign to do. There we go. Something like that. 9.8. What units? Meters per second squared. Yeah. That's how you get 9.8. You use the mass of the Earth, the radius of the Earth, gravitational constant, and that's why anywhere on the surface of the Earth, the gravitational acceleration due to gravity is right at 9.8 meters per second squared. Okay. Example 220 then takes us another. What would the value of G on Earth if Earth were less dense, that's with the same mass, but double the radius? Okay? So now the formula would be, goodness, I hate to write this again, 6.67 times 10 to the minus 11, and that would be Newton, which is kilogram meter per second squared, times meter squared per kilogram squared. That's Newton meter squared per kilogram squared, times 6.0 times 10 to the 24 kilograms. That's the same kilogram as before, divided by but twice the radius. The radius was, remember we did 6.4 times 10 to the 6th meters. That is 12.8 times 10 to the 6th meters. But then we're squaring that. Okay? Now, that's really not scientific notation. You should say 1.28 times 10 to the 7th, but we'll just leave it like that for now. So let's get my calculator back. Okay, 6.67 EE 11 minus times 6 EE 24 divided by, open parentheses, don't forget that this time, 12.8 EE 6 close parentheses squared equal. That drops the acceleration due to gravity to 2.4 meters per second squared. So if you double the radius, you divide the acceleration by 4. Inverse square law. If you do 9.8 divided by 4, you're going to get something pretty close to that. Maybe not exactly the same. Okay. Have we had someone new enter the class? Just had something pop up as if it did. They had 2.4 meters per second squared. Good for them. All right. Do you want to take, let's see, how is our time? 3:12. We only got 30 minutes to go to the lab. You want to take a quick break? I just need to get up and walk around a little bit or get something to drink. So I'm going to pause this for now. I don't think I can pause the Zoom, so it's just going to be silence for a while. All right, sorry about that. But ever since I've been this severely anemic, I just run out of energy so quickly. And I've been going, like I said, since 8:30 this morning. This is my 4th class. Okay. Let's move on to any questions on this so far? Are y'all awake? Okay.
Yes.
All right, we're here. So let's talk about the Earth satellites, the moon being one. So let me clear my ink off the screen. We talked about this. This is why satellites move around the Earth, because the Earth provides the centripetal acceleration, pulling them in. They have enough velocity outward to keep them from falling into the Earth, so they constantly move in a circular or near circular pattern. There's a blurb at the top of page. Now, like I told you before, I sort of skipped figure 2.28, which shows the Earth force of gravitational attraction decreases inversely with the square of the distance from the Earth's center. Note that the weight of a 70-kilogram person varies as the distances from the Earth's surface. On the surface of the Earth, he weighs 70 kilograms, which is he has a mass of 70 kilograms. That's a mass, not a weight. That has a weight of 154 pounds. Okay? You go up another 4,000 miles, which is about your 6,400 kilometers, and now the weight is cut by 4 times. So now he's down to 37 pounds. Double that again, and you got 3 Earth's radius there. So you're now 1/9 of what it was before. Now he's down to 17 pounds. Go another 4,000 miles up. That's at 12,000 miles. He's down to 9.5 pounds. Go another 4,000. He's down to 6.3 pounds. And another 4,000, which is 20,000 miles above the center of the Earth, above the surface of the Earth, and his weight is now 4.7. So even though they talk about weightlessness in space, they're not that far off. Now, if they're heading toward the moon, yeah, they get pretty close to being weightless, but you see, he's still at a few pounds. And you go twice that distance, and it's only going to cut it by 4 times, so he's still more than a pound. So you're never completely weightless until you're way out there in deep space, far, far, far from the nearest mass that would give you weight. So I was going to point that out to you. Notice the mass is always the mass, 70 kilograms, okay? But your value of G goes down just like you did before. It was 9.8 at the surface. By the time you're out there at 20,000 miles, it's only 0.3 meters per second square. Incredibly, incredibly small. Okay? Now, there's on top of page 53 another blurb. This is a closer look at gravity problems. And they're talking right there about the thing that they're never completely weightless. They're getting close to it, but not completely weightless. They're always falling toward the surface of the Earth because they're revolving around the Earth. But that makes them feel like they're weightless. Okay? But then problems with being weightless is that your muscles start to atrophy because you're not using them for anything. So that is really a good blurb, and it brings up the fact, can we really send someone to Mars? They're going to be so far away from the surface of the Earth for so long that we don't know if their bodies can handle it, especially on the trip back, okay? Once they get back, are they going to be able to walk? I mean, will they be able to do things like that? So that's their blurb on gravity problems. All right, now we move back to the Earth satellites ideas. And here we are, these are now artificial satellites, not things like the moon. These artificial satellites must travel more than 300 320 kilometers above the Earth. Now, if you go back to that table we had before, 320 kilometers above the surface of the Earth was not very far at all. Not very far at all. They're still, when they're there, they'd still feel like they were, you know, probably around 100 pounds if they were originally 154 pounds, maybe a little less than that. Okay? They must be more than 320 kilometers above the Earth. Make sure that was in kilometers. Yeah. Okay. They must travel at least 8 kilometers a second. Okay, now think of that. A kilometer is about 0.6 of a mile, so that would be about close to 5 miles a second. Okay, close to 5 miles a second. They are really moving. If they weren't moving that fast, Earth is going to pull them right down into its gravitational field. So that they have to go at least that far. And here's an example. This is GPS satellites. Now, the only way that GPS satellites can work is they've got to be in what they call geocentric orbit. In other words, they have to stay in exactly the same position above the surface of the Earth. Otherwise, they couldn't give you your GPS because if they're moving, there's too many variables there. Okay? A lot of your communication satellites, like if you have a dish TV or direct TV, stuff like that, that thing's focused toward a satellite, satellite is always there. It can't move, otherwise you don't get a signal anymore. Okay? So they have to be fixed in geosynchronous orbits. Okay? But you also have to have at least 3 satellites to determine your position. Because all a single satellite does is tell you you're somewhere on that circle. Now that circle there would be anywhere from northern Greenland, northern Canada, to somewhere past the, it looks like probably past the Great Lakes or somewhere in there. This isn't a very good map. Going deep into the U.S., coming out somewhere around North or South Carolina, and then heading out into the Atlantic. You have no idea where you are. You're just somewhere on that circle. Well, a second GPS satellite puts you on their circle, which has you either in Norway, Sweden, maybe the edge of Finland, somewhere deep into Eastern Europe, down in the eastern part of the Mediterranean, down into Africa, in the Sahara Desert somewhere. You're somewhere on that circle. Well, those two together tell you you're either in Iceland or you're out here in the middle of the Atlantic. Well, that's not really helpful. You hope you're not in Iceland. You hope you're warmer waters than that. But that third satellite tells you you're somewhere here. Now, that's not touching any land, just somewhere in the North or South Atlantic Ocean. And guess what? The 3 of them together pinpoint you to be right there. Right there. Okay? Now, those are examples of what they call artificial satellites, man-made satellites that we put up there, not that were there by nature. Okay? And I think, oh, here we go. Astronauts appear to be weightless, but they're still affected by weight. They can't be weightless. They're actually in constant free fall. They're falling toward the center of the Earth because they're not, you can see, they're not that far from the Earth. They're constantly falling toward the center, but because they are going the same speed tangentially that the spacecraft they're coming from, they don't realize they are, but they are just going in that circular orbit around the Earth. Okay? Pretty incredible picture there. And it's in your text as well. I think that, yeah, is the last slide. Now, there is a blurb in the book, a really nice, interesting blurb on Sir Isaac Newton. Now, you can choose to write on Newton, but this cannot be the source of your information. I've read this. I've read it many times. If this is what your paper is, you're not going to get a score for it because you can't use the text as your source. You have to go outside the text. Okay? There is also a blurb at the bottom of page 55 on apparent weightlessness. I'll let you read that at your own pleasure as well. Then we have the summary. Now this summary is about maybe an average length. Quite a few italicized words in it, and we'll get to those later. But look at the equations. At least 12 different, totally unique equations here from this chapter. And many of these can be written as 2 or 3 other equations, like average speed is distance over time. You could write that as distance is equal to average speed times time, or time is equal to distance over average speed. So that one equation is actually 3 equations. You could say the same thing for 2.2. You could probably write that as 3 or 4 different equations. Then 2.3, that would be another 1 or 2. 2.4, another 1 or 2 perhaps, maybe 3. 2.5, you could do at least 2 more equations for that one. 2.6, the same thing. 2.7 pretty much is 1. 2.8 you could write 3 different ways. 2.9 you could write 3 different ways. 2.10 at least 2 or 3 different ways. 2.11 also. 2.12, wow, lots of formulas. Now, when you were talking about the italicized words back in the summary, you'll see most of those over as key terms. Now, to me, this list is a bit shorter than normal. They're written in, given in alphabetical order. However, they give the page number on which they're first defined or described. Then you have applying the concepts. And this is maybe about normal, maybe 1 or 2 fewer than normal. 47 questions here. If you know the answer to those 47 multiple choice questions, you're going to be well on your way to doing extremely well on the test. And again, the test is mostly multiple choice. Not those same questions, but they're going to be testing you over the same material as those questions. So if you know those, you're going to have a good clue of what the others are. Questions for thought, I think this may be a 1 or 2 short of normal. For further analysis, maybe 1 or 2 more than normal. Okay. There's a interesting little invitation to inquiry there about the domino effect. I'm not going to worry too much about that. The parallel exercises are a lot like the examples that were given in the text. I'll let you work on those yourself. I asked them to put the answers in the back. However, I don't think they did of the small text you have. I don't have those texts, so I don't know. So that brings us to the end of chapter 2. Normally, I'd be saying your test would be the next time we meet, which would be a week from Tuesday. A week from Tuesday, because next Tuesday is spring break week. But I'll try to get your test to you so you can use spring break if you have free time, which I'm sure you will, to work on that so you'll be able to accomplish it. So let's move on into chapter 3. We're not going to get too far, but let's go where we can. So I'm going to exit this slide. I'm going to try to exit this slide. If I could get the slide to come up. There it is. I'm going to discard that, sorry about that, and get rid of that slide. And I hope I don't lose you here. As screen sharing stopped. So I think I did lose you, didn't I? So what I'm going to have to do is do OK here and share. Okay. Let me go to this chapter. Maybe not. Let me try this a different way. Share screen. That'll get it to us, I think. Chapter 3, that's it. That's the one I want. There we go. All right, I see Jacob up. Did you need anything, or you just happened to pop up here? We'll go from current slide. Now, say again? Okay. I can't hear if you're saying something to me. I'm going to try to get this box out of the way. I know Jacob's on his iPhone, or it looks like it is. I see somebody's ceiling fan turning. I don't know whose that is, but that's all I got there. Okay.
Cash.
Oh, it's that Cash? Okay. All right, let's go from current slide. I thought I did that, but it didn't come up. There we go. Can everyone see the slide now? Okay, good. So here's chapter 3, energy. Now, if somehow to you forces were sort of a nebulous quantity, something you had trouble getting your mind around, but you have a fair idea what that is. And then momentum might be a little tougher to picture, but it's sort of if you're having trouble picturing those, energy usually gives more people more problems with that. Now, I'm not just talking about students. I'm talking about physicists. For the longest time, there were huge arguments on what exactly energy is, because it's not something that is all that intuitive. We talk about it and we act like we know what it is, but my goodness, it's a tough thing to wrap your head around. And here's the core concept, and it sort of has a little bit of a hint for what's going on there. Energy is transformed through working or heating, but the total amount of energy remains constant. It looks like we've lost a couple of people. We're down to 15. So anyway, energy is transformed through working or heating, but the total amount of energy remains constant. Let's go back to that first picture here. What's happening there? What is that? Do anyone know what that's called? Anybody? Common name for it is a wind farm. What do they call it? What's happening here?
They're getting energy from the wind.
Exactly. The wind is blowing. Now, the wind blows for several reasons, but one of the major reasons is because the Earth is spinning, okay? And the atmosphere doesn't spin as fast as the Earth does, and that makes the wind blow, okay? Now, there's other things that come along in the play, too. Differences in pressure, differences in temperature, other things. But the main reason is that, well, my internet connection's unstable. I'm going to let that go away. Main reason is because the Earth is spinning. Well, that's just happening anyway, right? Well, we're harnessing, wind farms harness that kinetic energy of the wind, because the wind is blowing, making the turbine spin, and that then generates electricity. Hey, can you get any cheaper electricity than that? Well, it did cost a certain amount to install the wind farm, but the actual source of energy, it's there. We're not having to pay a dime for it. It's the production of it is what costs. Okay? Now here we have another thing. What does that represent? Anyone know?
Dam.
That's a dam. Hey, watch your language. Okay. That is Glen Canyon Dam on the Colorado River. Now that's just one of the many dams on the Colorado River. The biggest is the Hoover Dam. Wow, someone dropped something. Is Hoover Dam, which has behind it Lake Mead, which is an enormous lake. And what both of these dams are doing, any idea?
Gathering hydroelectric energy.
Exactly. They're using the energy of the water. Now, the water is piled up on the other side of the dam at a much greater height than it is on this side. And then as the water falls through the dam and turns water turbines, as opposed to wind turbines like the wind farm had, turns water turbine, the kinetic energy of that water, which comes from the potential energy of the water up at the top, when it falls, it picks up kinetic energy. That kinetic energy is then used to turn the turbines and make electrical energy. Same type principle as before. Energy is transformed through working or heating. That energy, the wind energy, is doing work on the turbines, and that's transformed into electrical. Here the potential energy of the water in the upper part of the dam, when it falls through the lower part, the kinetic energy there. And by the way, since water is much more massive, it has more kinetic energy than wind, and that's turning powerful water turbines, and they're producing electricity as well. But the total amount of energy is the same, but it's changed form from potential energy to kinetic energy to rotational energy to electrical energy. I mean, it's just changing forms all the time. That's why it's hard to get your head wrapped around energy. It's always changing. Okay, here's the fundamental law, and this law is the conservation of energy. Just like we had conservation of momentum in the last chapter, we have conservation of energy here. In fact, momentum and energy seem to be sort of closely related. They're not exactly, but they are some. Now, the interesting thing is this slide seems almost out of place because I didn't think they talked about conservation of energy until they got way later in the chapter. Yeah, energy conservation is talked about on page 75. We're on page 62 and 63. But this is just an introduction. Here are different manifestations of energy. Work is actually a manifestation of energy. In fact, it's the use of energy, you might say, produces work. Motion, that's what I was calling kinetic energy, the energy that came, the wind's motion, the water's motion, that is motion that is called kinetic energy. The energy of position, that was when the water is in the upper part of the dam at rest. When it falls, it loses its potential energy due to position, gains kinetic energy because it's picking up speed as it falls. Radiation is light energy, or not just light, it could be any kind of electromagnetic radiation, from radio waves to gamma rays, so any kind of electromagnetic radiation like that. I think there's something that follows that, but my block there is blocking it. Then you have chemical energy. I'm looking outside right now, and I see these little green leaves that are coming out on the trees. A few trees already had green leaves on them. They were evergreens. What do those little green leaves do for us? Anything? Yes. Well, they produce oxygen, but the reason they do produce oxygen is those little green leaves, and when they become bigger green leaves, they do it even better. They suck in carbon dioxide from the air through stomata, holes, pores that are in those leaves. They pull up water and some nutrients from the soil, okay, suck that up from the ground, and in those little green leaves you have chlorophyll. And chlorophyll is the active agent in producing photosynthesis. Photo meaning light is taking that radiation, light energy from the sun, and converting that into chemical energy, taking that carbon dioxide from the air, water from the ground, combining that together and forming carbohydrates. Sugars, simple sugars, complex sugars. If you have a fruit tree or something like that, we have a pear tree. Most of the squirrels eat most of them, but we get a few every now and then. But the sweetness of that fruit comes from the carbon dioxide in the air, the water from the soil, and that produces that photosynthesis, takes the energy from the sun, changes it to chemical energy, making new chemical compounds, sugars, that then later we eat and we metabolize those sugars. That gives us the energy to do what we need to do. Read, listen, work, take out transmissions, whatever you're doing, that provides the energy you have to do that. And that's a chemical process itself. Now, nuclear energy is one we have very little control of. Most of that's happening on the sun. That is exactly what's happening on the sun. That's what's producing the electromagnetic radiation that we saw from light and other sources. The nuclear energy is when a nucleus is either blown apart in fission reactions or combined together in fusion reactions. That's what's happening on the sun. And that, but in our nuclear power plants, it's fission. Big molecules are breaking into smaller ones, releasing enormous amounts of energy. Okay, so there's another kind of energy, nuclear energy. Mass itself is a form of energy, surprisingly. But I bet you, all of you know the formula that relates to that. Do any of you? I bet you do, you just don't realize it.
Y equals mx squared.
E is equal to mc squared. Exactly. Einstein's famous relativity formula. This is mass here, and this is energy here. So a little bitty bit of mass from here multiplied by, anyone know what C is? What that C is? Anybody? Speed of light. The speed of light. Speed of light is, I'm going to give it to you in common units, 186,000 miles in a second. Okay? If you were on the equator and you were able to fire a photon of light around the equator and it would circle the equator, it would go around the equator something like 4.5 times in 1 second. I mean, that is fast. So that's a huge number. Then you square that number, it gets even bigger. I mean, way bigger. Multiply that by just a little bit of mass and you've got an enormous amount of energy. Okay? Incredible. That is how mass converts to energy. Doesn't happen often. That happens in nuclear reactions, basically. So, what are some of the sources for our energy? Well, for many, well, probably close to a century or more, we relied on petroleum. Before that, it was coal, though we still rely on some coal. More recently, we've been, and this is a long time back too, moving water. I'm not just talking about hydroelectric dams. The road that our house over in Georgia is on is Story Mill Road. Well, where did it get its name? Well, a guy named Story had built a, dammed up a McBean Creek and put a water wheel there, and the water falling over the dam turned the water wheel, and they used that to grind the grain and the corn and stuff like this, make cornmeal and flour. Moving water was used to do work. Nowadays, moving water is used for hydroelectric energy, okay, producing electricity. Nuclear, we talked about that. That's either on the sun, which we're going to get to in solar in a minute. So let's just talk about nuclear energy here on Earth, and that's when you have these huge fission reactions where they take big molecules like uranium or plutonium and split them into smaller ones, and that gives off an incredible amount of energy, mostly in the form of heat, and they take that heat to boil water, because all your nuclear power plants are usually on rivers, and they boil the water and make superheated steam. That steam fires through the turbine and makes electricity. So that's the whole purpose of nuclear power plants, okay? Solar energy is also nuclear energy, but that nuclear energy from the sun, which is fusion reactions, even more powerful, and we just get a small, tiny, tiny little amount of that reaches the Earth's surface. We can convert that into, with solar cells or other things like that. If some of you have a just a regular old scientific calculator, I bet you there's 3 or 4 little panels at the top, usually at the top. Those are solar cells. As long as you're in light, whether it's natural light or room light, you know, it is converting that light, solar, photoelectric energy, into light energy into electrical energy to power your small calculators. If you have a great big old graphing calculator, you're having to charge it, or it's running on batteries or something. But the others are running on light, actually. What are some of the uses for energy? Whoa! Well, let's let this slide and we'll be through. Transportation, generation of electricity, heating, cooling, lighting, anything you can think of, okay? Manufacturing. There's just tons of uses we have of energy, and always coming up with more. All right, that we sort of beat that slide into the ground. We will start next time with work, and this is beginning of 3.1. All the rest of it was overview, introduction. All right, so I'm going to end the slideshow there. Okay, and unfortunately I didn't think to open, well, let's see, I'm going to do this now. Oh no, I think I've got it open. So I'm going to close this PowerPoint, and it's going to knock you out for a minute, I think, not literally, but okay, let me close this slide. We'll come back to this after spring break. So now the sharing window is closed, but let me see if I can get it open again. Oh, I have to hit OK for that. I don't see my, oh, there it is. Of course that's what I want. Oh, wait, I think I did that wrong. Can you see this?
Yes.
You can see this blackboard?
Yes.
Oh, okay, good. So that worked. Okay. So I'm going to take you through how to do this lab. I also talk about the other one for any that didn't get to see that. Okay. I'm into Blackboard now, and I don't know how your Blackboard looks, but this is mine. And going down here to, here's the course content, syllabus, locator card. Y'all did that in your first lab, remember? Research paper, general instruction, YouTube videos, PowerPoints. This one wasn't up there then because I didn't know we were going to end the term and go to online. So here's your laboratory simulations. Click on that. That takes you to a link. And when you get here, you go up here to simulations. And right now we're doing physics simulations, so go to physics. At some point here, Cash, you said that it told you it wouldn't do anymore, right?
Yeah, this I'm confused there, so you sure I'm walking through it right now with you on my laptop.
Okay, and it's doing all that I'm doing so far.
Mm-hmm.
Okay, good. Did it get this far before or not?
I never did go this far because I didn't know what to do.
Oh, okay. Okay, well this may get you there then. So I'll take you to the first lab first. And that was the moving man. Now it's alphabetical, so keep on going down till you get to moving man. Okay. There we are. What's that?
I found it. This is Tarsha. I finally got mine to work.
You did. Fantastic. Okay, excellent. There's the moving man. Say again?
Is all of our labs going to be in there?
I can't hear well. Say again?
Is all of our labs going to be on there?
I think so until we're back in the classroom. So, yeah, I got to keep finding them. Here's the lab number 2. Your 0 lab you did the first day of class when I wasn't here. The lab 1 we did in class, I think the last day we met. Okay? Here's moving man. This is lab 2 now. Okay? And you get here and then you hit download. And it takes a while to download, so be patient. You'll see down here, sometimes we'll say it can harm your computer. It never has, so I'm going to keep it. Okay, you have to watch down here and see if it's through loading. I think it is. So then click on here and see if it's through. Well, you don't see it doing anything. It takes a while, so be patient with it. Don't give up.
Okay,
Okay.
Dr. Fowler, for
Yes.
me, I did not click on the word download. I actually had to click on the picture.
Oh, you did? Okay, that may work too. Here, finally, moving man is starting up. See, it took a while. And then you get to this. Now, I couldn't get this particular thing to do a thing. So I went this is introduction. Now, maybe you can figure out something to do with this. I couldn't. But just notice this. The blue is your position vector. The red is your velocity vector. And the green is your acceleration vector. Then go to, say again?
I don't see anything.
I don't see it. We're not seeing it.
You're not seeing anything there.
See a blank screen or whatever.
Okay.
It's just blue.
Oh, you mean,
The screen's blinking, it's blue.
okay. Well, then what I think I have to do is go back here. No, it's still showing that it's sharing. You can't see anything on the screen. Can anybody see this picture of the man looking up into the sky and there's a green tree and a brick wall? Does anyone see this? Can anyone see this picture?
No.
No. Okay, let me try.
Might have to take it out of sharing and reshare or something.
Okay. Let me try. You say stop share?
Maybe. And do it again.
Okay, let me stop share. And let's share screen now. And let's see if I can get, there's moving man. I've got two moving men.
Can I tell you what mine is saying?
Okay, what's yours saying?
It said this file type is not supported. Please visit.
Say again?
Okay, that's what I'm on. It said this file type is not supported. Please visit the Chrome web store to find an app that can open this type of file.
Okay, well, that way you would actually have to download the latest Java.
Okay.
Okay. I hope y'all can figure out how to do that. Can you see this slide now?
I see that.
This one that says download moving man, that one?
Yes.
Okay, now if I hit the download, which I did before, let's see if you can see that one. Again, it says keep. Now, it takes a while on this one, so be patient. Are y'all trying this on your computer as well, or are you just watching mine?
Just watching yours.
Okay. Takes a while. Well, it's taking a long while. I'm getting impatient. Let me try this again. There it is. Okay, moving man is starting up. Do you see that now? No.
It's a blue screen again.
It's what?
It's a blue screen again.
Blue screen again. So let me try another one here. I'm going to stop the share and go back to share screen. This time I'm going to do, which one? I think I hit this one before. I'm going to hit this one this time. Do you see them now? Okay. Got him. All right. Everybody can see that now.
Yep. Yes, sir.
Okay. Once you get this, here's where I was saying. The blue vectors you're going to see are your position vectors. Your red are going to be your velocity vectors. And by the way, position is measured in meters, velocity in meters per second, and acceleration in meters per second squared. Okay? This I couldn't get to do anything that made any sense. So I went to the charts. Okay? Now you get this. You see that one? Now I'm going to show you what I did. You can do this. I think I demonstrated this before, but here's what I am going to do now. Let's take the man and make him go in negative direction, turn around and go in a positive direction. I can't see where he hits the wall here, somewhere over here. And then, oh, there he went. Now he's back in the negative direction. And now he goes back positive. I'm just doing this to play with him. You can play with him however you want to. I don't think he hit the wall that time. Okay. Keeps going. And keeps turning around again. Keeps going. And back again. You see, every time I move my finger, he stops, he starts. So he's changing things. I'm awfully close to the end. All right. Now what I do is do a playback. And that freezes the screen. So stop it right there. Okay? Now, remember, this is his position. He started here, went negative, went positive, went negative, went positive. Every time he passed 0, he was back on this dotted line here. That's the equilibrium position. Now, what I wanted you to do in this is to note what your velocity is doing, how that relates to the position. And it relates in some sort of strange ways, but they're very regular ways. Can anyone see a pattern right now?
As position goes negative, velocity goes down.
Okay, when the blue line is going downhill, you're in negative velocity. When the blue line is going uphill, you're in positive velocity. And then when it's going down, yeah, okay, you pretty much have it there. Now, and you play around, get them to do whatever you want to do, but then you describe what's going on the way you see it. You can start them going to the right first and to the left, whatever. That's your first lap. Make me a picture of this, print this out, screenshot, whatever you want to do with it. You can either have it as an electronic file or a paper file, however you want to do that. If it's paper, then turn on the back of that paper and write what you just described there. How does the blue line relate to what's happening with the red lines? How does the position related to the velocity? Now, I can't make I can make out some sense of the acceleration, but I doubt if you can. And I kept saying before, ignore the wiggles and squiggles in here. Just look at the general pattern of your velocity, general pattern of the velocity. What the wiggle and squiggle is when I was having to change, swipe my finger over and over. Every time you had a little change here, that was showing up big time here. So ignore the wiggle and squiggle part and just talk about what it's doing on the overall here. What's happening? What is your velocity every time you change direction? That's another good question you could answer. Now, looking at this, however the velocity accentuates these little minor changes in the acceleration, in the position, the acceleration is magnifying those in velocity. So every time the velocity changes from up to down, you have a 0 on your acceleration. But that's way too difficult to see. So forget about acceleration here. Just focus on position and velocity and write down in a sentence or two how those two are related on the back of your paper. If you email it and send it to me, if you do electronic copy and you don't even print this, then type on a piece of paper that relationship between position and velocity. Does that make sense? And if you want to, if your first time didn't do too well, you wanted to redo it, all you have to do is, I think, hit this button again, and then you start playing again. Okay? No, it's just doing the same thing that I did. It's just playing that same thing over again, I guess. I think
So, just to reiterate, make sure I have this down. We just need to make him some movements and then screenshot it, and then describe what he's doing, or what he's done?
Yeah, especially relate the position to velocity.
Yes, sir.
And what the pattern is there. Okay? So all I'm doing is replaying what I just did. But if you want to replay for sure, you hit the clear button. That takes you back here. Okay, now the clock's still moving. So what you do is reset all. Okay, reset all settings. Yes. And then you start over. And then you get the man and you move him wherever you want him to move. Okay? I'll tell you, the first time I did it, mine was a lot more awful than that last time. Okay, it gets a little better with practice. So you may want to clear and reset all and then start over again. However you get it to look to your satisfaction, and then explain what you just saw. Okay?
Okay.
All right, with moving man. Okay, I'm going to try to get them to close without closing anything else. So I'm closing moving man. Okay? Ups, and that ended that, didn't it? Okay, so what I'm going to do now, you probably have a blank screen again, right? Okay, so what I'm going to do now is minimize this, and, well, you know, I just hit the wrong thing. I thought I was closing moving man, but he didn't close. Okay, let's go back to simulations. Y'all can't see this, or can you? You can't see my screen? Okay. Let me see if I can get it back on again. Have I ended Zoom?
No, we can still hear you loud and clear.
Okay, so I must still be on Zoom. I don't want to quick Zoom. All right, let me get rid of this. Oh, I think I see it. Okay. Trouble is, oh, there's return to meeting. Sorry. I was on the screen. I just couldn't tell what it was. Okay. Let me get my squares. Okay. I think this is the one. This is the one I go back to. Okay. Can you see that? Can you see anything on your screen? Okay, good. All right, now I'm going to go back to simulations, physics, okay? And this time we're going to, I think it's ladybug, okay? I tried to find one that sounded a little more intriguing than this, but the one I went to gave me absolutely nothing. Ah, there it is, ladybug motion in 2 dimensions. See, what we were doing with the man was one-dimensional motion. He was just going back and forth in 1 dimension. Here we're going to have ladybug moving on us. Now I tried to do the one down here that was motion in 2 dimensions. I couldn't get it to do a thing. So if maybe you could, if you want to, you can try it. But ladybug did something, so that's where I'm going now. Okay. It takes a while to load. Okay. I don't think I want to do that. I don't remember getting this screen before. Oh, here we go. I don't remember getting this screen before. I don't know. I hope I don't have to contribute to use it. Maybe they let me use it last time to see what it was like. Are y'all seeing this screen too?
Yes.
Okay. And I don't know how. Let's see. I'm going to try to end that screen, and I'll probably lose you again. Ah, let me try this. There we go. Okay, ladybug motion. Download, there we go. Can you see this screen? Okay. We're going to keep it. And I bet you I'll lose you here. Let's see. Again, don't get overly I don't know what's the right word for it. I can't think of it. Don't get upset if it takes a while, because it does. but I'm getting impatient. That's what I'm getting. So I'm trying to try it one more time and see if we can upload it now. Opening Ladybug, it says it is. Ah, there we go. Oh, the trouble is, okay, there we go. All right, here's Ladybug. Have I lost you?
Yes, you're going to have to do what you did before.
Okay, so let me go back here. So frustrating. Okay. And I think it's moved up here. New share. Is that it? I think so. Let me try that. Yeah, okay. Now, which one worked before? I think this one
See the
does.
blue screen again.
Okay, can you see that?
Okay, yes.
All right. So here's how you get here. Now, the trouble is this is in the way. So I'm going to move. Do y'all see this file, the block I'm moving now? Maybe I only see that. Okay. Over here on the right, we have vectors, and I've got show both. That's velocity and acceleration. And it says choose the motion. I want you to choose 3 of them. The first one I want you to do is circular motion. Okay? And there goes the ladybug. Okay? Now the velocity is the green vector and the acceleration is the pink vector. And I want you to describe for me how they are changing. Are they changing in length any? Are they changing only in direction? Or both direction and length? Those are the questions to ask. Okay, number 2, which way is acceleration always pointing? It's changing always, but what does it always point to? That's a good question. And that goes with circular motion that we did in the text today. Okay, and velocity, it's also always changing, but where does it always wind up being? The answer to that is, I can't get a cursor to show up here. Notice the velocity is always tangent to the circle, okay? But it's always the same length. So circular motion, write down those things that you note about circular motion. One of them is, how are velocity and acceleration related to each other? Are they changing relative positions? Are those, what about that angle between them? What would you say? They're always changing, but is the angle ever change? Between velocity, the red one, and pink, the acceleration. Does that angle ever? No, the angle doesn't change, but the directions always change. What is that angle?
It's the right angle.
That's our right angle. You're absolutely right. And velocity stays a constant length, acceleration a constant length, but they are always changing direction. Which way does the acceleration point? And which way does the velocity point? Okay, I'll let you answer those. Okay, now, ellipse. Sort of like a circle, only a little bit different. Here is an ellipse. Now again, my thing is in the way. What do you notice about velocity and acceleration now? Wait, maybe first the acceleration vector. Always changing direction, but is it changing its length now? What you think? Acceleration.
Yes, the length is changing.
Yeah, it's sort of like a turtle. It's janky, pulling in its head and sticking out its head, okay? Now, when is it the longest? When is it the shortest? I'll let you figure that out. Okay, how does that relate to velocity? Is velocity changing? Its length? What you think? Yeah, getting shorter and then longer. Where is it the shortest and where is it the longest? Okay? And is there any relationship between the length of the velocity vector and the length of the acceleration vector. Okay? Those kind of things. Just anything that grabs your attention like that. Now what you go to after you've written up a little bit about that, oh, and by the way, I forgot to tell you, now, you can pause that somewhere and take a picture of that. So I'll know you did see this, okay? Or print it, or however you want to do that. And then on the back of that one, answer your questions about acceleration of the ellipse. Do the same thing for a circular. I forgot to say that. When you're doing the circular motion, okay, I'll let the circle draw itself. Get the ellipse fade out. Okay, I'm not going to let it do, but you can stop that at some point and then take a picture of that and explain to me either on the back of that picture or wherever, you know, and tell me what's happening between acceleration and velocity. Okay. Then we go to manual. Okay. Manual, you get to move Ladybug around. So here's what I did. You can do whatever you want to. Whoa, I went off scale. You'll have to play around with it and get better at it than I am. Okay. But try to do a path here, some sort of a path here. Try to stay on the screen. I'm not doing a good job of it. Okay. Whoa, I went really bad there. Okay. Anyway, we'll stop there. And let's do playback. And start the playback. There it goes. Okay. And you can stop anywhere you want to. It's not a good place to stop. Right there. And explain what's happening. Okay. Now, obviously there, acceleration almost in the opposite direction of velocity. So what's the velocity vector doing right after that? If you caught that, it got shorter. I let it go too far. So anyway, play around with that, take a few shots, explain what's happening. Now here the velocity and acceleration are close to the same length, but you can't see it well because it's off screen. So that's why you need to stay on screen. Whoops. I must have played too much. Okay, I don't know why it's not moving anymore. But anyway, oh, that's where I stopped it, I guess, before. So anyway, play around with manual. Get a better picture than I did. Keep it in the screen if possible. And then notice what's happening, the relationship again between velocity and acceleration. When is acceleration the longest? When is velocity the longest? When are they going in the same direction? What happens then? When are they going in opposite directions? What's happening then? When do they seem to be close to perpendicular to each other? What's happening then? So those are the kind of questions to look at and answer. I know it's sort of vague, but do enough to let me know that you have done it, taken some pictures of it, or printed them, whatever you want to call that, and that you sort of understand the relationship between velocities and acceleration. And again, for the manual one, when you can get a better picture than I did, last night I got a better one than this, say what is happening when they're going in the same direction, when they're going in opposite directions, when they're close to perpendicular to each other. Where are you in the path? Where are you on your track? If you can sort of set up a track and run the track, see if you can figure out what's happening then. Does that make sense? Sort of, a little bit. You think you have enough to go on lab?
Possibly.
What's that?
Possibly, yes.
Okay. It should be fun to play with. Don't get too bogged down with it, but play with it enough that you feel like you're learning some physics from it. Okay? And this is two-dimensional motion. All righty? Any other questions? I can't think of anything else to do to keep your time, so I'll let you work on your labs. I can stay online if you think you're going to have questions, or you can work at your own pace and then email me whatever if you get hung up.
I'm gonna have to download the latest Java like she said, and then
Okay, say that one more time.
I'm gonna have to download the latest Java like Tasha said, and then I have to play with it.
Okay. And if you have problems with it, I think, as I told you before, Miss Jamie Glass might be able to help. She's probably working from home. She may be down in Montgomery. I hope she's not, but she's been going to Montgomery a lot, working on Banner. But she is really good about trying to answer questions. So if you can't figure out how to get something loaded, she can probably help, talk you through it, or give you.
I email you, and I email Tasha.
What's that again?
If I have issues and I can't reach her, I email you, and I email Tasha.
Okay, you can email me and what?
And I email the other student, Tasha.
Okay, something about other students, but I couldn't make it out.
I email them also.
Oh, okay, yeah. They'll probably be better answers than mine would be, because I have to call my wife and say, how do you do this? Okay. I'm a dinosaur, okay? All right. Any questions?
No, sir.
All right. Well, I've enjoyed good class today. And what I'm going to do now, you know the good news, bad news situation, right?
What's that?
Well, the good news is next week is spring break week, right? But the bad news is that means we won't be meeting either Tuesday or Thursday. So can you get over it? Oh, no. Yes. Get over it, guys.
What will we do?
Yeah, what will you do? Okay. But we'll meet again, both Tuesday and Thursday of the following week. That's the 31st, 1:15 again. I'll try to have the code for you sometime between 12:45 and 1:15. That's my only lunch time. And so as soon as my 12:15 class is over with, I'll try to get it set up for you, and then I'll leave it, go down and grab the bite or so to eat, and then get back up here by 1:15 as possible. But don't leave without me, because I will be back. Okay?
I have a question.
Yeah, what's that?
Did you mark me president?
Who is this?
Tiffany.
Oh, no, I didn't catch you. Welcome. Okay, let me get Tiffany here. And by the way, let me get everybody for lab. So let me call roll again for lab. I'm glad you said something. Drew never showed up, did he? Carpri? Lydia? Cameron? Brianna? Is Jacob Dove still there? You are, aren't you? Yep. Okay. Kaya? Didn't show up, did she? Sam, you still there? No Sam? Tarsha's still there. I just saw her.
Yes.
Is Gunner still there? Say again? Okay, Gunner's still there. Eric Hill never showed, did he? Zach Hogue? Don't think so. Jeff Jones still here? Yeah. Good. How about Kurt Jones? Did we lose Kurt? Oh, okay. I thought I saw him. I must have seen him when he went off. Did he catch any of the lab, or do you know? I don't think so. Edward, you still here?
Yes, sir.
All right, good deal. Katie, I don't think ever made it. Mrs. Lewis didn't make it, did she? Jason, you still here? Jason? Yeah, Jason's still here. Ian?
Yes, sir.
All right, I thought so. Josh?
He's still here.
All right, good deal. At least he's got a friend anyway, okay? Zane still here? Zane? Was he here during the lab?
He's on here. His name's showing.
Oh, okay, good. See, I don't see the names. I don't know why I can't see the names. I see them one at a time when they speak. Okay, David Nash never showed up, did he? Anaya, I don't believe ever showed up, did she? Jacob Porte, still here?
Yes.
All right, good. Jose, you still here? Did we lose Jose?
He's on here.
He is? Okay, good. Thanks. Tiffany, I know, is still there. Perrin, you still here? Perrin. Did we lose Perrin?
He said his computer died.
What's that?
He said his computer died.
Oh, okay. Was he here for any of the lab? Do you know?
I think he was here just a second ago.
Okay. How about Cash? You still here?
Yes.
I thought so. Okay. Chad, you still here? Did we lose Chad?
Doesn't show him.
What's that?
It doesn't show him.
Okay. Did we lose him before lab?
Not sure.
Not sure? Well, okay. It really doesn't matter much anyway. Y'all are all been in present. All right. Any final questions?
Yes, I do.
Okay.
Okay, you said I see something on here about a paper.
A research paper? Is that what you're talking about? Yeah.
I'm concerned about the topic.
About what?
I'm concerned about the topic. I didn't know we had to write a research paper in the science class.
Okay. You didn't do that first lab?
No, I wasn't here the first day because I had just enrolled in it, and then I didn't do the first lab. So I was here. My first lab was the second lab, the one that we just did.
In class with the circles and the cubes and that kind of stuff?
Only lab I attended, the last lab we just had.
Okay. And you didn't get a copy of the first lab? It was called the Zero Lab, Lab Zero.
Okay.
Did you get a copy of that?
No, I did.
Okay. I will send that to you via a text, email or something like that attached to a thing. A few people I knew didn't get it, or I was afraid didn't get it, so I was going to send that. My wife has to scan those, and if when I can get them scanned, I think she's going to her office tomorrow. She hopes nobody will be there, so she can get in and get out. So she's going to scan them then. I'll try to email them tomorrow afternoon. But that tells all about or if you go to the YouTube videos, the first one that says syllabus,
Okay.
it was one from last term, but everything's true about the paper that was true last term. The instructions from the paper, they're out there under Blackboard, and basically you choose any topic that has to do with physics, chemistry, physical science, anything to do with any energy, forces, nuclear power. I mean, anything to do with physics, or you get to choose your topic. I haven't seen any papers come in yet, I don't think.
I wanted you to do name a few examples.
What's that?
I said you did what I wanted you to do. I wanted you to name a few examples of what kind of paper that I would do.
Right, okay. So that's answered your question?
Yes, that answered my question.
Good, okay. And all the specifics are out there on the files. Okay. Any others? Good question, by the way.
When we do our research project, do you want us just to email it to you?
Yeah, you're going to have to do that. And let me say this, I think I said it earlier, but maybe not everybody was on then. I do not anticipate at all that we're going to be back on campus by the 4th, 5th, 6th, 7th, whatever that is, April. I don't think the virus is still going to be expanding like crazy. I don't think we've even close to the worst of it yet. So I think we're going to be doing this for the rest of the term. I think as someone said earlier, both UAB, University of Alabama, they've already said they're not coming back this spring. In fact, they're not even holding graduation. Now, I don't know if Lawson will do that or not, but I think Alabama and UAB both said it'd be virtual graduation because they just cannot risk having that many people together that close.
Alabama University is also closed till the end of the
Who is that?
Alabama University
Yeah.
is also closed for the rest of this
Right. And so I can't see that Lawson will be opening back. But we might. But I'll tell you this too, that our last day on campus was Monday, and I got a phone call Monday night. No, actually, yeah. I think I got the phone call on Sunday night from the dean. she said, don't even come to campus tomorrow. I said, I've got to pick up all my materials. She said, oh yeah, that's right. You would have to, wouldn't you? So they did not want, because of my health situation, they did not want me back on campus. So even if the school opens back, I bet you they're going to tell me to stay at home, and we'll be doing this for the rest of the term. I think. I don't know that for a fact, but that's my guess right now.
Well, I mean, it's better if you stay home and we try and do this, and then you risk compromising your health just so that we can be there in person, you know?
Yeah, but I miss seeing your faces. Oh, all right, let me get off that. It's getting too deep up here. Okay, never mind. All right, no. I thank you for the...
Well, doctor, if you come back to campus, then my face may be the last one you see.
Right. So, yeah, thanks for that, because I don't think my wife's going to let me go back to campus anyway. So, anyway, it's even though she wants me out of the house now, I'm bothering her. She's downstairs in the office, and I still make too much noise up here. So, anyway, my guess is we're not going to co-pack, but we'll be prepared if we do. We'll be prepared if we don't. Okay?
Yes, sir.
All right. Any other questions? Good questions.
When is the paper due?
Okay, the paper's due before the last day of class, not the final exam day, but the last day of class. But it's far better to get it in earlier than later. And I think I put on there that if you get it in the month of March, you get 2 bonus points. We only got a few days left in March. Well, a week. You could
go ahead and email it tomorrow.
Okay, and if you get it in the first 3 weeks in April, you get 1 bonus point. But if it's after that, you don't get any bonus points. You just get your score. So the sooner the better. I'll put it that way. Okay.
What about these 2 labs?
The labs. Okay. Let's go over that. The lab 0. If anyone still hasn't turned that in, that's due as soon as you can get it to me.
I'll have it because I wasn't here. So
Right. I've got to get you a copy of it because you said you didn't get a copy, right?
Yeah, I don't have the.
Okay. Yeah. I'll get it as soon as I can. Okay. Lab 1, if you were there for that one, then you can send that to me anytime. You can send it, you should scan it and send it as attach it to an email. If you can figure out a way to put it on Blackboard, just let me know where you put it and I'll try to find it there. I think an email would be easier or better, but I don't know. See, this new Blackboard, I don't know how it operates. So far, it hasn't operated as good as the old Blackboard. What's that?
Just email both of them to me if you can.
Yes, that's perfectly fine. If you haven't done the first test, I will be emailing you a copy of that. Okay. If you test, the lab we just did, the moving man lab, when you get that, either print me a copy or do an electronic copy and send it to me. However you're going to do it, attach it to an email, whatever. But be sure you answer a few questions. What did you notice about it? The type of things we talked about. Then the ladybug lab, as soon as you get it ready. You always have at least 1 week after we do the lab before it's due in. And since we got spring break in the middle of this, the moving man lab is due the Tuesday we get back from spring break, and the ladybug lab due the Thursday after that, 2 weeks from today. The rest of the time it'll be 1 week. However, if you can get it to me sooner, that way I can grade it and get your grades out there sooner. Okay?
How are our tests going to work when it's online?
Okay, say that one more time.
How are our tests going to work when it's online?
You know, they're all going to have to be take-home tests. Sorry about that.
What a shame.
Yeah, I know. Get over it.
Dang.
Yeah, shucks. Okay? But we'll live through it. Are y'all okay with that?
Oh, I'm just heartbroken, Doctor.
Heartbroken, I can tell, yeah. Well, just, grow up here. Okay. No. All right. Good questions, by the way. Any others? Good deal. Well, y'all have a great spring break, but be careful. Be safe. Don't get out in crowds. Don't get out if you can help from getting out, okay? Because it's just...
I'm already wearing my hazmat suit.
What's that?
I'm already wearing my hazmat suit.
Okay, good. Okay, I'm glad I can't see your picture. No, never mind. I didn't say that. Okay. All right. Any others?
No, sir.
All right. I'll be signing off then and end the session. Y'all did a good class today. Way to go. We'll see you Tuesday the 31st. Okay? Any others?
No, sir.
All right. Bye-bye.